Hello everyone, welcome to the second set of videos on complex integration. This set of videos will cover quantities on Cauchy residue theorem. The first part covered on Cauchy fundamental theorem or the Cauchy integral theorem. This second set of videos will teach you or will explore on the quantities like poles, residues, Cauchy residue theorem and how to evaluate the value of the integral using Cauchy residue theorem. Come on, we will get started. The first thing we will be seeing is what is meant by residue of a complex function f of z. The value which is given by 1 by 2 pi I integral over the closed curve C f of z dz. This estimation or the evaluation of this part of the integral with 1 by 2 pi I is called as the residue of the function at any particular point called as A. So the next thing is how to evaluate these residues. There are going to be two types of poles or singularities which we have already seen. The one which is going to be of called as referred as simple pole when you write it of the form z minus a the whole to the power of 1 or simply z minus a. So we have to estimate the residue at a simple pole called as z is equal to a. The residue r is given by limit z tending to the particular point A, z minus a times f of z. So what happens over here, this function f of z will involve the function z minus a. When you allow the limit to z to a and you multiply by the factor z minus a, the function f of z minus f of z which contains z minus a gets cancelled off, evaluating the value for the remaining points of z at the particular point called as a. What happens at a multiple pole z is equal to a of order n? So this is nothing but z minus a the whole to the power of n. So if you have a pole of order n at the point called as z is equal to a, then the residue is estimated as limit z tending to a 1 divided by n minus 1 factorial d power n minus 1 by dz power n minus 1, that is the n minus 1th derivative, z minus a power n into f of z. Now also this f of z will contain a z minus a power n. When you multiply by this factor, this value of the factor will get cancelled off and the remaining quantities will be estimated at the value z is equal to a. So the two formulas which we'll have to remember or memorize in this section will be what is going to be the residue of a function at any particular point or a simple pole z is equal to a and at a multiple pole z is equal to a of order n. So if these two formulas are memorized, then we are ready for the set of formulas, set of problems to be carried out in this set of videos. Now coming to Cauchy residue theorem. If f of z is analytic at all points inside and on a simple closed curve C, except for a finite number of isolated singular points which we refer as poles and named as z1, z2, z3 up to zn which lie within C, then integral over the function C f of z dz will be 2 pi I times summation of all the residues of the function at these poles z1, z2, z3 up to n. So if I am going to have a closed curve called as C, and let this be my C, the function f of z is analytic at all points inside and on the simple closed curve C, but at certain points their derivatives doesn't exist. So there are going to be finite number of points inside where the derivative does not exist. These points are referred as poles. Let them name it as z1, z2, z3 up to zn. Now what do? Is we estimate the residue at each of these poles and then add them up, sum meaning add them up. So we add up all the residues of your function f of z at the poles. So what are the poles? Poles are nothing but the points where the function is not analytic, and then multiply by 2 pi I, in which case this gives you the value of the integral in the closed circle or the closed contour called as C. Now moving on, we will try determining the pole of the function f of z, and also we will try to find what is going to be the residue at each of the poles. So this will now be our problem number 1. The first step always is to determine the pole. How to get the pole of any given function? This is got by equating your denominator to 0. What is my denominator over here? Z plus 2 into z minus 1 the whole square. When I equate this to 0, what happens? I will have z plus 2 to be equal to 0, and we will have z minus 1 the whole square to be equal to 0. This first quantity gives me z as minus 2, and the second quantity gives me z is equal to 1, but it is not of power 1, but it is going to be of power 2. So z is equal to 1 comma 1. So z equal to 1 twice. Now this pole which is going to take power 1 is referred as a simple pole. So we call z is equal to minus 2 as a simple pole. But z equal to 1, which is going to be of power 2, is called a multiple pole of order n. And what is going to be the order n over here? N is going to be equal to the quantity or the power over here, which is 2. So I refer z equal to minus 2 as a simple pole and z equal to 1 to be a multiple pole. So now I have estimated the poles of the function f of z as asked in the first part. What is the second part? They are asking me to find the residue at each of the poles. So I need to find the residue of the function at z equal to minus 2 as well as residue of the function at z is equal to 1. Come on, we will evaluate them one by one. The first thing we are going to see is going to be step 2, residue at the simple pole. What is going to be the simple pole for us? Z is equal to minus 2. Z is equal to minus 2. What is my function f of z? My function f of z is z square divided by z plus 2 into z minus 1 the whole square. Z square by z plus 2 into z minus 1 the whole square. Now what kind of pole do we have? We have a simple pole. Now we need to find the residue at the simple pole. Now it's time to recollect the formula for the simple pole. We see the formula for the residue at the point z is equal to a. What is my point z equal to a? Now z equal to minus 2 to be equal to limit z tending to a. So z tending to minus 2, z minus a. So z minus of minus 2 will become z plus 2 into my f of z. This is how I will be getting my residue at the point z equal to minus 2, which is a simple pole. So now this gives me limit z tending to minus 2, z plus 2. When I multiply this with the function f of z which has been given to me, I will have z square divided by z plus 2 into z minus 1 the whole square. Now we can see automatically the value at which we are finding the pole will be removed from the function before applying the limit. So this value will be cancelled off by multiplying it with the factor. Now we are ready to apply the value. So apply z moves to minus 2. Wherever I have z, I'll have to replace it with minus 2. So minus 2 the whole square divided by minus 2 minus 1 the whole square. Minus 2 the whole square, 2 square makes it as 4 divided by minus 2 minus 1 is minus 3, the whole square is 9. So we have the residue as 4 by 9. So I have got the residue at the simple pole. What is the next task for me? I need to also find the pole residue at the second pole. What is the second pole? It is the point z is equal to 1, but it is a multiple pole. So the next target is going to be, we will add a slide to find residue at the multiple pole z is equal to 1, which is of order 2. Okay, so what is going to be my function f of z? This is z square by z plus 2 into z minus 1 the whole square. This is my function f of z. Now it's time to recollect the formula for residue at a multiple pole. So we will do it. The formula says residue is given by limit z tending to a 1 by n minus 1 factorial d power n minus 1 by dz power n minus 1 z minus a power n into f of z. Now what is required? We want residue at z is equal to 1. My n is equal to 2. So this is going to be limit z tending to a which is going to be 1. 1 divided by, this is going to be n minus 1. So 2 minus 1 factorial d to the power of 2 minus 1. 2 minus 1 makes it as 1 by dz power 1. Z minus 1 the whole to the power of 2 into my f of z. So now this gives me limit z tending to 1. 1 divided by 2 minus 1 is 1 factorial. What is 1 factorial? 1 factorial is going to be 1. I have d by dz of z minus 1 the whole square into f of z. Now when I multiply this with my f of z, we can automatically see that this factor will be vanishing because this function has a pole of order 2 at z is equal to 1. Now this factor and this factor will be cancelled off before we move on to apply the limit. Now what is left out? I have d by dz of z square by z plus 2 left out. So we will now move on to the next slide to find limit z tending to 1. The derivative has to be estimated. D by dz of z square by the quantity was z plus 2 over here. So we will try to apply differential of u by v, which is v square v du minus u dv. So this will be z plus 2 the whole square. Z plus 2 you keep it as such. Differentiation of z square is 2z minus u, that is z square, you keep it as such. Z plus 2 on differentiation is going to be equal to 1 plus 0. So this is going to be my derivative. Now what I have to do to my derivative? I will have to apply limit z tending to 1 to my derivative. When I apply limit z tending to 1, wherever I have z, that gets replaced by 1. So this becomes 1 plus 2 into 2 times of 1 is 2 minus this is 1 the whole square. So that makes it as 1 divided by 1 plus 2 the whole square. So that makes it as 2 plus 1, which is going to be 3. 3 2s are 6. 6 minus 1 divided by 2 plus 1 is 3. 3 the whole square is going to be 9. So this makes it as 5 by 9. So the value of the residue at the multiple pole z is equal to 1 of order 2 is going to be 5 by 9. We will try our hands on one more problem. The problem goes like, find the residue at each pole of the function f of z given by z square plus 1. The first point in any of the case is going to be estimation of the pole, which is given by denominator equated to 0. So I have z square plus 1 to be equated to 0, which gives me the pole. This is going to give me z square to be equal to, take this 1 to the opposite side, so it is going to be minus 1. So what will be z? Z will be equal to plus or minus square root of minus 1. So this becomes z is equal to plus or minus, what do we know about square root of minus 1? It is going to be equal to I. So what are going to be my pole? Z is equal to I and z is equal to minus I are going to be the poles of my function f of z. So I can rewrite this z square plus 1 is equal to 0 as z plus I into z minus I. So that is how my denominator gets converted as. Now notice that this power is 1, this power is 1. So what do you think is going to be the nature of these poles? Both these poles, z is equal to I and z equal to minus I, are going to be simple poles. So both of them are going to be simple poles of my function f of z. Now what is my target? The second target is to find the residue at each of these points. So first we will find part 2, residue of the function f of z at the simple pole z is equal to I. First we will copy paste our function f of z. What was our function f of z? Z by z square plus 1. Z square plus 1 now has been factorized as z plus I into z minus I. So this becomes z divided by z plus I into z minus I. So this is going to be my function. I want a simple poles residue. Now it's time to recollect the formula for your simple pole. What is my formula? Residue at z is equal to a is given by limit z tending to a, z minus a into f of z. So I have this to be equal to limit z tending to, what is my pole here? I, z minus I into my function f of z. So this is limit z tending to I, z minus I into, what is my function f of z? Replace it or copy paste it from over here, z divided by z plus I into z minus I. Now we can see automatically this point at which we estimate the pole will get cancelled off, leaving you for substitution for the other point alone. Now it's time to replace the quantity wherever I have my z with the point called as I. So I am ready for my replacement. Where is the first z? This is going to be replaced as I divided by z will be replaced as I. This already has a I. So you have I divided by I plus I, which is going to be 2I. I and I cancels off, leaving you with the quantity 1 by 2. So what is going to be the residue of the function f of z at the point z is equal to I? At the point z is equal to I, the pole has been given as 1 by 2. Now it's time for the estimation of the residue at the second point. What is going to be the step 3? Step 3 is going to be the residue of your function f of z at the simple pole z is equal to minus I. First we estimated for plus I, now we estimate it for minus I. Now copy paste your function f of z, which is z divided by z plus I into z minus I. And the next thing to do is going to be copy pasting your formula from your memory for the simple pole. We have the formula to be limit z tending to the point A, z minus A into f of z. So now we have this to be equal to limit z tending to minus I, z minus of minus I will become z plus I into f of z. Now copy paste your f of z, limit z tending to minus I, z plus I into z divided by z plus I into z minus I. Now the point at which we estimate the pole will automatically be cancelled off, leaving you with a substitution only for the remaining point. Now you can substitute the value to be equal to minus I for all the points of z in the given function. So you have the numerator to be equal to minus I divided by denominator is minus I minus I. So it is minus I divided by minus 2 times of I, minus minus cancels off, I cancels off. Again this leaves you with a remainder called as 1 by 2. So finally we have estimated the residue at the simple pole z is equal to minus I, also to be of the factor to be equal to 1 by 2. So the only requirement which is required from this session of video is to recollect the formulas for residue for simple pole and multiple pole, which has been given by this set of formulas. Limit z tending to a, z minus a into f of z for a simple pole. Limit z tending to a 1 by n minus 1 factorial, d power n minus 1, dz power n minus 1, z minus a power n into f of z. In the next set of video, we will see how to apply Cauchy residue theorem for evaluation of integrals. Thank you.